Good morning, everyone. Welcome to Physical Chemistry 4. Let us continue with the lecture. Just to reorient you, remember we are in the second chapter of this course, and so far we've covered these subchapters, and right now we are in the subchapter Parity. And yesterday we introduced or we reviewed the four basic forces in nature, and we'd like to expand on this today. So in particular, we had the weak forces or weak interactions, and this was related to left-handed fermions, right? So electrons are fermions, of course. And so the question is if and how they are related to the electromagnetic forces, which pop up in the macroscopic world through Maxwell's equations, and of course which govern through the postulates of quantum mechanics also electrons and thereby all of chemistry. Now there is a factor of 10 million or so in terms of strength, right? And so you might wonder if this is relevant. But seeing the large number of microscopic particles we are dealing with, this could indeed be relevant, and also seeing the long time periods which we sample in the age of the universe, which in which matter has been formed, and you could expect some manifestation of some interaction between these forces in the way how matter presents itself to you. In particular, there is this hypothesis out there that it could be the weak forces that are responsible for the fact that in nature you will exclusively find left-handed amino acids. Okay, I don't know if you ever wondered about this. Why should they all be left-handed? But it's certainly a fact, and people working on this, it's not solved to the best of my knowledge, but by the mere fact that this is a reasonable hypothesis, you can already see that this should be of concern. In any case, for our lecture, we will of course not study these weak interactions. They are quite complicated, but you do have to consider this fact: what happens if you apply symmetry operations, and one of the simplest symmetry operations is the parity operation. And this is something which is also deeply connected to the anti-symmetry condition, which the fermions, the Fermi statistics, according to Pauli, requires us to do. So we need to think about the effect of exchanging coordinates on the sign of the wave function. Okay, and that's precisely something this parity, this subchapter attempts to do. And so we ought to note that first of all, space itself is not, well, does not have parity, meaning meaning it doesn't matter if you choose, if you're living in a right-handed or left-handed reference frame. And so thereby you see the importance of chirality. So and the in particular we for fermions you should always think of Pauli. We need to consider the behavior of the electron wave function, that as you exchange coordinates, you should observe a change in sign. Right? So this is where parity is relevant. And what you will see later on is that something you're very familiar with, such as the nodal structure of the electron orbitals, is intimately related to parity operations. So let's start by wondering what is the operator, right? So, okay, yeah, so from the fermionic nature of the electrons, we will get to the nodal structure of the orbitals. Okay, so as usual in quantum mechanics, right, when presented with something like this, we first have to wonder what's the operator. Right? So first you need the operator. If you don't even know the operator, you cannot do anything. Once you have the operator, we have to wonder what is the wave, the eigenequation, right? What are the solutions to the eigenequation of this operator? So what are the eigenfunctions in which this operator lives, right? And only once you have those, you can actually calculate the eigenvalues and make some statement on what you would expect to measure, right? So this is the natural order of things. And so when we ask what is the parity operator, then very similar to spin, in this case, there's no classical analog, right? So we cannot use the correspondence principle. Right? The correspondence principle is beautiful because you can immediately construct operators that take the job, right, which you would have in classical mechanics. They take it over and you can use them in the quantum world, but it's not the complete set of all possible operators. Right? So it's insufficient to describe the entirety of quantum mechanics, which governs your electrons. So you do need more than that, right? It's certainly the necessary set of operators, but it's not a sufficient one. So what is the parity operator? So in analogy, or just like for spin, there is no classical correspondence. Right. So in other words, Houston, we have a problem. We need to come up with something for ourselves, and this is in general, this is tricky, but we can discuss specific examples. So, for example, we would like this operator to invert things, right? We talked about left-handedness, and so this would be something you'd like to see, that the parity operator, now let's call it capital Pi, it works on some function which has variables such that after it has done its job, we are somewhere else in the coordinate system and exactly at the mirrored position. Okay. This is quite easy to grasp, right? If you have a coordinate system and then you have a point somewhere here at x, y, z, right? Now that would mean we simply mirror it to, hang on, this arrow, this axis is exactly in the, so if this is your point, right? Here's my vector r, and basically it gets mirrored to the other side. So now you're in the minus x, minus y, minus z. Okay. And so if you have a function that depends on this r, right, then what you are basically saying is once I shifted my point of interest to the other side of the origin, that function value has to be the same, right? So if I plot the function value, now of course I just do that for 1D, right? So if I'm here at my x, right, and I have some function value, and then I do that inversion to minus x. Now the function value is supposed to be the same, right? And hence parity, right? That's the very meaning of the word. All right. So for example, suppose I apply my parity operator to a function which is x squared minus c times e to the ay. Then you simply go in, you put minus x squared minus z e a minus y, right? And so that would be simply x squared plus z e to the minus ay. All right, so we now sort of in a hand-waving fashion have introduced this operator, right? We don't know how it explicitly looks like, but we know what it does, right? And actually, it's as long as we can define that operation, right? Its function, we don't need to know more details of it, right? So we can leave it as it is. It's sort of an implicit operator. But we can ask the next question, right? I told you, right? The next question then is, what are the eigenfunctions? Right. Okay. So what are the eigenfunctions? And this is not clear really, but the idea is you apply pi to some function, right? And you should get the same function. But when you apply pi to any function, by definition, it should give the function value at the inverted coordinates. Right? So that's not necessarily the same function. So the question is how can we do this? And actually, there's a trick we can do, right? So the problem is if we apply pi to f of x, we do not recover f of x, but f of minus x, okay? But what if we apply pi a second time? Then we have this, and that would give us f of x back again. Okay. So we know that what this means is that pi applied twice corresponds to the unit operator. Or the identity operator. It will just regenerate what you've had before. Right? So that would just give 1, right? As an eigenvalue. And so basically what we then, so we can demonstrate this, right? So suppose it operates on some eigenfunction gi, then we have an eigenvalue. We don't specify it, but then we operate again on this. So pi squared working on gi then would give you, now this is the eigenvalue ci, would give you ci pi squared gi, and that thing must be ci squared gi, and because of this we know that ci squared equals 1, right? And hence ci must be the square root of 1 plus minus, which is plus minus 1. Okay. So those are the two eigenvalues possible eigenvalues of our parity operator. So we didn't solve the eigenfunctions yet, right? We don't have the eigenfunctions, but we already have the eigenvalue. So if you have an eigenfunction solution, that's what you should get in terms of eigenfunctions. So let's maybe the title should be eigenfunctions and eigenvalues. A little bit more precise here. So then we can ask this question, okay, let's now, for the eigenfunctions, if we apply pi to gi x, y, z, then as we just said, this one must be plus minus 1, so plus minus gi x, y, z, but also through definition of how our operator works, this must be the same as gi minus X minus Y minus Z. Right? So by definition, of pi. So this means we can distinguish these two classes, right? So for Ci equals plus 1, we find that Gi x y z equals Gi minus x minus y minus z. So that would correspond to this example I have given here, right? And then for Ci equals minus 1, we would find that minus Gi x, y, z would correspond to Gi minus x minus y minus z. So that would mean in this example above that you're mirroring things down here, right? Or here. So this we call an even function. This is an even function, and we give it typically the shortcut for even functions in quantum mechanics is a small g for gerade, yeah. And this is the odd function. This would be ungerade, G and U. So often in quantum mechanics, you specify electronic states. You indicate that behavior of your orbital using as indices G and U, and now you know where it's coming from. Okay, it's a result from these parity operations, which we have to consider due to the symmetry inversion, inversion symmetry, which Pauli has given us. Yeah? So if you wish to blame somebody for this, call Pauli. Now, this is pretty easy. Once you've agreed on this, this is pretty easy to understand. So an even function is symmetric with respect to your function axes, right? So typically the ordinate, right? So that is your function, and that is your variable, right? Then something like this would be even. So you can put a G. While something which is symmetric to the origin is what we would call odd. So for instance, now this is put the G here, so it's here. Now, what you can immediately see is that if you integrate from minus infinity to plus infinity an odd function, this must be 0. Okay. And that's, if you've been wondering why is he telling us this, who cares, right? That's super important, right? Your entire integral will vanish, right? And we come back to that later. But this is, of course, when you write down your matrix elements, right, of some function, and just by the nature of the parity, you can recognize that the entire matrix element has disappeared. It's worth a lot, right? So then you can save a lot of calculation. Now, can we know something else? I'd like to come back to the last theorem we discussed on the eigenfunctions. Right? Remember, when operators commute, they share the eigenfunctions. So it's very natural for us. The eigenfunctions to the Hamiltonian are our orbitals. Right? This is where the electrons live. Right? So these orbitals are the eigenfunctions of the Hamiltonian. So this parity thing has to work for electrons, which are in these orbitals. So if you are wondering now, can we learn anything about these anything else about these eigenfunctions, right? The most plausible, the most natural question to ask then is, well, does this parity operator commute with the Hamiltonian? Because if it does, they share these electron orbitals, right? So let's look at this, right? Do H and phi commute? All right, that's an easy job. We write this, and we wonder if this is 0. Now, we know what H consists of. There's the kinetic operator. And the potential operator. Right? Now, this kinetic operator has these prefactors, h bar squared over 2m, and then you need to differentiate twice, remember the curvature, in each dimension. And we can write that out . In this way. All right, so that means we have to wonder now, what does this differential operator do to our parity operator? Right? So that is something we can look at, and so let's start right? So consider this. We do our parity, we operate our parity on dx squared times the function of interest. Okay. So that means we have to differentiate, and differentiation in the limit, right, is nothing else than a fraction of an infinitesimally small variation. So you can change the sign of that variation, right? And you do that twice, right? And here is our function, right? So now parity has operated on this bracket here, right? Now, f of minus x is certainly the same as pi f of x, right? So the question now is this the same as the curvature set, right? And in fact, it is. So you can write it like this, right? Think about it. You're doing some variation in your function over minus delta x, and then you do it again. Right? So basically, you're dividing. You have like a division or multiplication with multiplicative operation, where in both cases you have a negative sign. So that is then the same as that, right? And that is the same as that. So in other words, on the right-hand side, you can see this, and that tells you that your parity operator commutes with the second order differential operator, and hence it does commute with the kinetic operator, right? So you can do the same for y and for z. The prefactor doesn't matter. So this whole bracket must be 0. Okay. All right, now what about the potential, right? So what about the part? Here we can do the same story, right? Same trick, right? So consider pi acting on V, and now I write my V directly in all coordinates, and some F. Right? So that F should be the orbital. That's where the electrons go. All right, what does that do? Well, so pi operates through, right? And so I have V minus X minus Y minus Z, F minus X minus Y minus Z. Now, if your potential is an even function, right? Now, is this a crazy idea? Just think about the harmonic oscillator. Think about the potential of an atom, right? It's radially symmetric. So if you change to the opposite, if you do a reflection, you will recover the same. So if you do a rotation around your function, you recover the same v. So it's symmetric with respect to your ordinate. And so this is certainly a case we should consider, right? It's not always the case that your potentials are even, but it's certainly a possibility, right? So if v is even, then this is equals vx y. You see, just as in the kinetic operator case, and this again is pi applied on f, and hence for an even potential, h and pi commute. Now, this brings me to our theorem number 6. If v is even, there's definite parity in your electron orbitals. These are all electrons, yeah? So that's a crazy thing, right? So we did this back on the envelope, hand wavy sort of derivation. And now you can say something about any electron as long as it's in an even potential, right? What does definite parity mean? It means that here you have, right, if you consider your pi, right, you know that this pi works on f, and that means f is either even or odd, right, because of our two eigenvalues. So your orbitals have to be, or have to have, either even or odd symmetry. Okay. So there has to be the symmetry in the orbitals, right? So, for example, consider the particle in the box, the quantum harmonic oscillator, or the H atom. Consider the solutions to these quantum problems. You know these eigenfunctions already, right? You know already that they have this symmetry, right? But now you know why. So far, it just emerged out of your ansatz for solving Schrödinger's equation, right? But now you have a physical reason for that, not just a mathematical derivation. So just to illustrate this further, you know this picture. This is your even potential, and then you have the equidistant eigenvalues, and you know the for the harmonic oscillator, and you know your ground state. It's a Gaussian, right? That's obviously the even function. And then you know your bad at drawing these things. You know your next function is odd. And then you have again an even function. Etc., etc. And every solution to every level will be either even or odd. That's quite a statement, right? It's incredibly general, right? All right. So,
sorry.
Yes.
I'm just trying to understand what you exactly tried to do when you wrote "consider this," and then showing that they commute. I mean, I do see you're trying to prove that they share eigenfunctions, right?
That's why we are looking at the Hamiltonian, right? We are talking about the electrons, and the electrons live in the eigenfunctions of your Hamiltonian.
Yeah.
And we know that they must obey Pauli's symmetry condition, right? Which is why, so this is manifested then in this parity operator. And so we now want to see the effect of this on your solutions to Schrödinger's equation.
Mm-hmm.
Which you see already just by solving it, but when you just solve when you just consider the solutions of the quantum harmonic oscillator, you just look at them, you recognize that symmetry, right?
Mm-hmm.
But you don't know why it's there.
Yeah, I meant the paragraph where you wrote "consider," and then you wrote you're trying to prove something, but it doesn't really make sense to me.
This one?
Yeah.
So here we take from above, right? We take this bracket, okay? If you consider this commutator, then it's okay, so that commutator is this minus this, okay?
Mm-hmm.
And so it contains this term, right? It's the same as this one. So we are looking just at this first term and we are transforming it. And then we see on the right-hand side now, here we see actually that's the same as this one.
Mm-hmm.
And hence they must commute.
Okay, yeah. Thank you very much.
No problem. Thank you for asking this question. Right? It's in my experience, it's always the case if one of you ask a question, you're not the only one asking this, and so it allows me to clarify. All right. So that is we first showed this for the kinetic operator, right, and then for the same spiel for the potential. Right? So that allowed us to arrive at our theorem 6. Let me look. Oh, it's exactly 10 o'clock. I have one more remark to make, but I'll do that next week, and then we will be done with parity, and we will move ahead towards the next subsection, which is called measurement and superposition. So this is about how these eigenvalues, which we obtain by solving eigenfunctions, which obey to all these theorems we discussed so far, how they are actually then related to measurement, and how the probabilistic picture of quantum mechanics actually emerges from all of that. So if you have any further questions, get in touch with me by emails or with your assistant, Mr. Trestman, and I believe you have still another exercise tomorrow. I hope things are going okay, and if not, just let us know, okay? I'd like to thank you for your attention, and I'll see you next week.
Thank you. Goodbye.